the classes, I'll tell you the same thing. I started teaching in August of 1980, and I am getting old. And unless I look at the mirror, I don't realize I'm getting old because I still think I'm 12. At least that's what my wife thinks, because I behave in a similar way. But I think that's okay. So I started teaching over 41 years ago. That's a long time doing anything. And I'm still enjoying it, go figure. So, what's the Calc 2 going to be about? Well, let's tell you Calc 1. If somebody said abbreviate Calc 1, I would say something like this. It started off with a problem called the tangent line problem, where you're trying to find a way of getting the slope of a tangent line to a curve at any given point. And after a lot of work, we solved it. And the solution to that ended up generating differentiation. And then what Calc 1 was about was, how do you differentiate functions? And so we learned product rule and quotient rule and chain rule and, you know, trig differentiation and all sorts of cool stuff like that. And then the last part of Calc 1 was, okay, now you know how to differentiate things, do stuff with it. And the kind of things you could do with differentiation was find slopes of tangent lines, obviously, but couldn't you also use it to find velocities, accelerations? And didn't we also use it to optimize things, right? What size would be the best size to make a box to have the biggest volume? Or what's the, you know, what temperature does the chemical reaction happen the greatest at? Things like that, right? And we learned a whole lot of useful things that you can do with Calc, in particular differentiation. So what's Calc 2 going to be like? Well, we're going to start with a problem. And that problem is going to be, how do you find the area under a curve? The exact value, right? How do you find the area under a curve? And we're going to find out how to do that. And it's going to happen pretty quickly. When you did Calc 1, it took about a fortnight before you actually got to differentiate anything. Didn't you spend a lot of time doing limits and finding slopes of things, you know, numerically, and it got kind of boring after a while. But, you know, eventually we got to the end and, way, here's the shortcut method. The shortcut method is differentiation, right? And then off we went. Well, we're going to, in Calc 2, do the area under a curve. That's going to be the problem. But we're going to solve that really quickly. 2 days. That's it. And then we'll say, hey guys, here's the shortcut. Here is an algebraic way to get the exact value for the area under the curve. And then the rest of Calc 2 is going to be, how do you find integrals? Because integration is going to be the name of the shortcut process that does area under curves and other things. So you're going to find how to integrate things. And you're going to find techniques like substitution method and integration by parts and trig substitution and so on and so forth, right? You're going to have techniques, right, to integrate things. And then we're going to say, now that you know how to integrate functions, let's use them. And you're going to use them to find exact areas under curves. You're also going to use them to find velocities and accelerations again, different way, but you're going to use it. You're going to use it to find volumes of shapes, surface areas of shapes, arc length, and all sorts of applications like hydrostatics, which is to do with water pressure. So if you're a submariner, you might be interested in that. And we're going to do, you can use integration to find the amount of work done. So if you're an engineer, you might be interested in that. So it's going to be how to do integration and then how to use it. And that's kind of the flow. So that's the big picture. That's what we're going to be doing. So let's look at the syllabus and get that over with. And then we can get a little bit about how the course is going to work. And then after that, hopefully get started on finding the area under a curve. So first things first, I am going to zoom over to the screen. I'm closing some windows here. Here we go. You should be looking at a Canvas site. Is that correct? Is that what you're saying? Okay, I think I'm on the wrong one, so let me make sure I go to the right one, not that there's a lot of difference between the two. I think yours should look like this. Yeah, should. Come on, there we go. And let's put it on a student view. Oh, right. So let's go into the syllabus. A lot of what I'm going to give you, you're going to get information overload, but will you remember that you can just go back to Canvas and read it anyway? So if I miss something out, or if I, if I jump by something quickly or whatever, you can just go and read it. So there's my email address. And this is bolded and highlighted in every other way I can think of it. When you do WebAssign, will you please not use the features in WebAssign like contact my professor, ask for help, ask for an extension? Any of those things in WebAssign are not good. I don't get that information, right? You just don't send it to me. All you do is, if you want help, if you want an extension to your homework, is you shoot me an email. And you can shoot me an email to drobertson@olympic.edu, or you can just use Canvas, because Canvas directly sends it to me anyway, so I get it. So if you have any questions, any help you need, anything else, remember to do that. If you use the WebAssign thing, you're going to think I'm ignoring you. Like, oh, I asked for help on question 7 and it's 5 days and he still hasn't got back to me. He's not paying attention to me. No, it's, I don't get that email, so I never knew you were asking me the question in the first place. Okay, so make that clear. Right, there's our officer. It's just before this class. That link will be valid for a couple of months. You should have the prerequisite. If you don't, Friday they'll send me out emails and I have to drop you. Here's all the good stuff that you need. Make sure that you've got all the tech that you have. If you click on this link, these are all the free resources. Olympic College will provide you with a webcam, with earphone, mics and all that good stuff. If you need one, they'll give you loaners. If you have financial issues that you might find it a little bit hard to keep, up with the course, Sing is a good resource. Cassandra, you probably know lots of other resources, don't you, to help students out financially?
I do know of quite a few resources that the college is offering. I don't know, like the Sing office is going to be really good for financial, like helping with acquiring the materials you need.
Right.
But off the top of, you put me quite on the spot here.
Don't worry, you can tell us tomorrow, right? But
Yeah, I can tell you
because
tomorrow. Or if you have specific questions, you can email me at ckramer@olympic.edu. That's my work email, and I can help you guys get where you guys need to be.
okay, there are lots of different resources. Financial, there's also psychological help. We have counsellors, because this is not a very healthy time in anyone's life right now. So I can understand if you're feeling the pressure. I think a lot of people are, but lots of resources out there. Our job is to try and help you, right? So I want to do that. Now, this bit here is basically how to log on to WebAssign, and I've already sent out an email, but that PDF there, which I'm not going to click because it takes forever to load up, has all the step-by-step instructions to log into WebAssign. Here's well, we'll show you it later, but there's a Zoom page, so if you have issues with Zoom. Right, here is the calendar with all the cool dates. If it's kind of yellowy colored stuff, these ones here, they're holidays. There's Thanksgiving, for instance. You can see right now there's 3 tests and there's a final. Let's talk about what we cover in this course. It's broken into weeks, 1 week slots. For instance, this week we're going to be doing these 3 sections, and the homework's due midnight on the Sunday, right? On Cassandra, if you hit the space button, it'll mute you so we don't need to hear you eating. I'm sure you do. Sorry about that. There's week 2. Here's week 3. And then after 3 weeks, we get a test on everything that's covered here. And then we do 3 more weeks and we have a test. And then we do 3 more weeks and we have a test. And then we finish off with the last 2 weeks are bumped together because that's Thanksgiving and a lot of these days are used up by holidays. And then Monday is a review for the final. And this class gets an exam, a final on the 9th. So you don't need to memorize this. I mean, you can go back and look at it when you feel the need. Learning outcomes, this is what we're going to be learning. Don't cheat. If you have accommodations that need, tell me about it. And then we'll jump on to the grading. First one is participation. It's mandatory to come to class. So you get points for coming to class for participating. And the way that we keep track of that is that you will go, and why don't we do it right now? Inside chat, just say hi. And that's it. I have now taken attendance. That was easy. And that's why it's a good idea to make sure your name is your name, because Fred42 isn't very helpful if I have to take attendance. Not that anybody here has got that, but you know what I'm getting at. Okay. Here is the Zoom link, hopefully the right one for this class. That's going to be the same link for the next couple of months. Homework assignments is all done in WebAssign. That's 30% of your grade. I'll talk about that later. Here are the tests I talked about. There's 3 of them, but the worst one gets kicked out. So the best 2 out of the 3 and you are good to go. So you can have a 1 stinker and it won't affect your grade. Final exam, 30%. And there's extra credit. And the way extra credit is going to work this time is going to be based on homework. Every homework that you do on time, that means you didn't ask for an extension, you get 0.5% extra credit. So you could get in total 5% extra credit. So if your grade ended up being 70%, that extra 5 would make you 75 and you'd pass. Right. Now, it's very hard to be perfect attendance, and I understand life gets in the way. So if you miss 2 or 3 days for your kid gets the flu, you have to go to the dentist, whatever it is, you just have a bad day and you just don't want to do anything, whatever the reason is, you can, you'll get dinged on the participation, right? But you can claim that back and more from the extra credit. So what I suggest you do if you miss a day is that you go and you look up the lesson, because I record all of them, and you look them up and you put, you know, you catch up on what you've lost, and that should put you in a good place, right? So you won't have missed anything too vital. Okay, here are what your grades look like. As GPA, here's the lettering, here's some useful resources, and the normal general advice like come to class, pay attention, participate in class, ask questions, things like that. And don't do your homework or anything 2 hours before Sunday midnight. That does not end well. Your homework is designed for a number of things. The 2 main reasons in my book is, the first one is when you take a lesson, you'll listen and you'll say, yeah, that makes sense, I can do that. But you don't really know if you understand it until you take the homework. And then you suddenly realize, oh, maybe I don't understand it as deeply as I thought I did. So that homework is a way of catching that. And second reason is homework's practice. The more practice you get at something, the more adept you're going to be at it. I mean, the analogy is you don't learn how to play a violin by watching people play violin, right? You don't learn math by watching me do it. You learn math more by you doing it, right? So that's the practice. That's what your homework's there for. So if you don't like homework, you got to think of it as something you got to do to get good at what you want to be good at. So that's important. And all the other cool stuff that we don't want to happen to you, or do, I guess, sometimes. Depends on if it's a good or a bad thing. Okay. Any questions about the syllabus before I move on? We good? Right, if you missed anything, because I skipped by a lot, can't you just read it and then send me an email? I don't know what this means, and I can try and explain it. Okay, let's leave that page and spend just a little bit of time on what you can get in Canvas, and then we'll zoom over to WebAssign, show you a quick summary of what's going on there, and let's get started. So, if you click on this one, you'll see a welcome one where I tell you a little bit about myself and some cool videos in there. How to set up WebAssign. If you click on that, it just tells you a list of all the things you need to do in week 1, week 2. It's an exact copy of what's in the syllabus. There's a resource page, there's your officer, and this one here, if I click on it, this is the classes link. And then if you click on this, here is where I'll be putting the Zoom lessons. Today's Zoom lesson, for instance, is going to go in that empty box there. And it's probably going to say something like syllabus and, study course and the day it took place. So if you miss a day, you'll find it in week 1 or week 2 or week 3. So I'm going to make an assumption here right now. And so I'm asking your permission. So you are allowed to say no, and you are allowed to say no. I want your permission to put the lessons that we do onto Zoom. For FERPA, I have to ask your permission. To make you feel a little bit better, although these are stored indirectly on YouTube, they are private. So the only people who can actually see any of these videos are you, right? So if that makes you feel better. So if you're not happy with that, you just tell me, and then I won't save the Zoom lessons, essentially. That's what I have to do, and I will do that. We're good? Right, so that's where your Zoom is. Now let's see what, that's okay. I thought I hit the wrong button. If you look at the next module called class resources, do you see a whole load of stuff here? This is just extra stuff. There's nothing here that you have to do or even look at, but I'm putting it here because I think it's useful and you might want to. For instance, if you click on this one, see section 5.1, click on this. Here are videos that I found either by other professors, or this one, for instance, is by me, that I think are helpful on the topic areas and distance. What you'll find here is other professors at different universities or colleges have done it. They explain it in their own way, and sometimes they've got much better graphics and visuals than I could ever do on a piece of paper, right? And you can go there, and it's another resource because, well, I used to be conceited, but now I'm perfect. But I understand that how I see things doesn't always work for every person in every situation. So it's very often a good idea to say, oh yeah, I like the way Professor Smith explained that topic. It makes more sense to my brain. And I have no problems with that because, God, we're not the same people, right? We don't see things the same way. Our brain doesn't process information the same way. And so it's helpful if you've got someone else's perspective on something. And that's what it's there for. So if a lesson doesn't make sense to you, or you just want to see another way of maybe doing it or looking at it, here's a resource for you. If you scroll down to the bottom, there's a PDF here, which hasn't came up right. The window should be bigger, but I will be fixing that. And I guess I could click on it. Yeah, let's say I click on this one. Yeah, yeah. When the thing is fixed, you will see this stuff. Here's a PDF, right? And it just goes over and gives you some examples of some help, really. That's basically it, and it's in the written word. And if I, get out of that, it hasn't quite been formatted properly, but I will fix it. I promise you sometime later today when I have time. And that's the class resources. And the other one was a PDF. And I wonder if it's in here. Yeah. And then hit this one, And this one is all the college stuff. So if you want to, a link to Canvas tutorials or tutoring or library services or whatever, right, here's lots of links to resources that we give. So I want you to think of the Canvas as a resource, right? A place you can go get extra help on anything, including the videos that have happened in the past. Any questions? Anything you're not sure about? Okay, nodding heads is good. I like that. Okay, next stop should be here. All right, and this is, I hope, what you will see when you get into Cengage, right? And if you've done WebAssign before, there is nothing new going on here. Do you notice that these ones here, these four assignments are what's going to get done this week, and these three are for week 2, and eventually week 3 and 4 and so on will be on the thing. Let's well, that's out of order, but never mind. Let's do that one. I'm sure I clicked on that. Try again. There we go. Essentially, a WebAssign is just homework. It's just like textbook homework. The only difference is that you type your answer in. So don't worry about this because it won't make sense because I haven't curved it. But let's suppose, I'll stop somewhere. Right, let's suppose I do this one. And I could watch a video. And I think the answer is, I'm making no attempt to tell you what the right answer here is. Right, let's suppose I thought that was the answer. And you put your answer in here, you put your answer in here, and you get to the bottom and you do submit answer. And if you're right, you get a nice green check mark, right? And if you're wrong, it's a little red X, and you get 5 shots. Right? You do your stuff. And let's go to another question. Sometimes you do questions. God, these are taking forever. And you can click watch it, which typically should be a video. And you can click read it, which will be, it typically sends you to the ebook at the location where this information is, and you could read over a bit of the ebook, and it'll give you an idea of how to do this very long-looking question. So, things to watch out for in WebAssign. Be very careful about what is very easy to miss. Sometimes, not in this particular question, but sometimes they say give the answer to 2 decimal places or give the answer as a fraction, that kind of thing. So you have to make sure that whatever they ask, you give it. So if the answer to 2 decimal places is 1.23, if you type in 1.2, it's going to tell you you're wrong. And I think even if you type in 1.234, it'll also tell you that you're wrong. So it's not a human being. It's pretty dumb. It's programmed in a very primitive way. So whatever it says, do it. If it says it wants a fraction, give it a fraction. If it says it wants 4 decimal places, give it 4 decimal places. Just keeps it happy, and it saves you getting a question wrong when you really did it right. You just weren't being careful about how you wrote the answer. Any questions? Are we good? Okay, then I am now going to return, and we can start the class. I'm ready. So 5.1 is what we're doing, and it's going to be finding the area under curve. Now, you don't need to write down everything that I'm doing. It's up to you how much or how little you write, because you can always go back and look at the video. You know, if you think, oh no, that's just too much, I can't write all that down. Well, you can just say ... and look at the video there. Right. Well, this is the initial problem that we were way back in the day, they were trying to solve. And it's, imagine I have a curve that starts there and it finishes at there. So it starts at x equals 1 and it goes 2, 3, 4, 5, 6. When we say area under the curve, what we mean is I want to find the area of this shaded region. Now, do you see that? Oh, that's got a bit of slope to it. Do you see that the area under a curve? Can I move this a little touch? There we go. Well, we have a problem with this, and it's caused by the curve, right? The function y equals f of x. Would you agree it'd be very difficult to get the exact area under that curve, right? That shaded area. If it was made up of straight lines and horizontal lines, couldn't we break it into little bits and add them all up? Because we know how to get triangles, we know how to do rectangles, we could do it. And if it was half a circle, we could do that as well. But when it's just a, you know, a random x cubed minus x squared kind of curve, you see, that's a big problem. And that's called finding the area under the curve problem. And that's where Calc 2 is going to start. And we're going to begin by doing a numerical estimate. So we're not going to get the exact value, that's coming later. Right now, we just want to get an answer that's close to the real answer, right? We want to find a practical numerical way in which we could at least do a guesstimate of it, right? So imagine, as someone once was, the first person to think this problem through. And they're going to say, look, it's got to be simple. It doesn't need to be perfect, but at least it's going to give me an estimate of that answer. And you might think, well, I wonder how they approached it. Anybody get any gut feeling how you might approach it? It might not be theirs, but that's fine. How you might approach this problem. While you're thinking about it, I'll do this. You all stuck? Nothing comes to mind?
With the areas that are easy. Start
So
with the areas that are easy, the portions of the area. Start with the portions of the area are easy, big rectangle, and then
oh, I'm sure you're saying something very interesting, but you're breaking up. So I'm going to kind of show you how they approached it, and it may or may not be the way you did it, and that's fine if it is or isn't. So there's one. I'm going to try and pretend that that's the same shape where you kind of pretend that it is. And we also pretend that that's the right scale. This is how they, one approach that they did. They said, okay, if a problem is big, why don't we split it into smaller problems? Can you pretend that each of these strips is the same width? Would you agree that the distance between here and here is 1 unit, and the distance between here and here, I know it doesn't look it, but if I did it to scale, wouldn't that also be 1 unit? Right. So I have split this shape into 5 strips. So let's introduce some notation. You will see very often n equals 5, and that means 5 strips. So what we're going to do is we're going to find an estimate for the area of each of these strips and then add them all up. Would that seem like a reasonable approach? Now, we haven't really finished solving the problem yet, but we're going to get there. One of the simplest shapes to find the area of is a rectangle. So what I'm now going to do is I'm going to take each one of those strips and make a rectangle that might not be the exact answer, and in fact it won't be the exact answer, but at least it's an approximate answer. So I'm going to take this first strip. Do you see this one here where my finger is? And I am going to choose a rectangle. And there's lots of places I could choose the rectangle's height from. Couldn't I choose the left-hand side and make my rectangle here? Or I could choose the right-hand side and make my rectangle here. Or I could even pick the middle and make my rectangle in the middle. Would you agree that those are three possible rectangles? In fact, all three of those techniques have been used. But we're going to focus on only using the left-hand side. So I've got the first strip and the left-hand side is here. So I'm going to use that. And that's going to be my first rectangle. And then my second one, well, I could use this height or this height, but I'm going to use the left-hand side. Third one, I'm going to use left-hand side. Fourth one, I'm going to use left-hand side. And last one I'm going to use is the left-hand side. Now, would you agree that I should be able to find the area of all those rectangles, right? Because they're just one unit by whatever the height is. That makes sense? And so if I found the area of all those and added them together, wouldn't that be an estimate for the exact value of the area under the curve? Now, some of my rectangles, this first one, isn't that a lot smaller than the real answer? And the second one is a bit smaller, but at least the third one's a bit bigger and the fourth one's a little bit more bigger. And then the last one is a bit smaller. So can you see some of the small ones get a little bit compensated by a couple of the bigger ones? Not perfectly, but at least a little bit. So there's a kind of balancing going on here. When you do strips like this, the width of the strip, that's the distance from here to here, is going to be called delta x. So whenever you see delta x, it's a number that represents the width of one strip. And when you do this technique, you always make sure that the strips are the same width. That's just to make numerical calculations a little bit easier. So far, so good? So let me see if I can very crudely come up for an estimate using these rectangles. Now, there are 5 of them, and each rectangle was formed by using the left-hand side of the strip, and they are called L5. So that's the notation we will use. 5 means there's 5 strips, and the L means for each strip, use the left-hand side to get the height, right? So you got a strip, use the left-hand side. Now, in this case here, it's going to be 1 times the height of 5. The second strip is going to be 1 times, call it 7.9. And the next one is going to be 1 times 8.5. The third strip is going to be 1 times 8. And the last strip is going to be 1 times 7.1-ish. Right, so 5, 7.9, 8.5, 8, and 7.1. So let's see what that gets me. 5, 14.9, 22.9, 23.4, 31.4, 38.5. And there's my estimate. Now, I'm not going to go through the entire working part. Secondly, the picture's going to get really ugly because of that. But I just decided, because I wanted to choose the left-hand side. Couldn't I have chosen the right-hand side to get the answer as well? And if I did, this first strip, wouldn't it be using that height? So this would be the height. And the second one, it would be that one. So this would be the height. In the third one, it would be a little bit lower. You see it'd be down here. In the fourth one, it'd be a little bit lower. It'd be down here. In the last one, it would be that guy up there, and it's up here. Now, as I say, that's a total mess. But can you imagine having two pictures, one beside each other? Wouldn't those red rectangles, they would be called R5. And couldn't I find width times height, width times height, width times height, width times height, and width times height? And I'm not making any attempt to, if this is correct, it's sheer luck. Can we pretend it's 41.2, just for an argument's sake, right? You know, you could go and, you know, check it yourself, but let's just pretend. Do you notice that it's different from the other one? Wouldn't it be remarkable if both answers were the same, right? They're made up of different rectangles. Some are higher, some are lower, and they don't always balance each other out. But at least don't we now have a numerical way of estimating the answer, of coming up with some numbers that are hopefully relatively close. Are you all with me so far? Right? Looking good. So here's a problem for you. I want a more accurate answer. I don't think 5 strips are good enough. I don't think 38.5, 41.2, somewhere in that ballpark number is the right answer. I mean, it's too big, it's too vague. What could I do to improve the accuracy?
More strips.
More strips. Doesn't more strips mean more boring? Doesn't more strips mean give me a computer program, please? If you're into computer programming, could you understand that it wouldn't be that difficult to write a program to do 1 million strips? It would be horrendously, nobody in the right mind would do it by hand, right? But couldn't you do 1 million strips? Being exaggerated, right? But if I did 1 million strips, and I'm making this up, but I did L 1 million. And let's say L 1 million came out as 40.0000007. If you were a gambling person, wouldn't you probably say that you think the right answer is probably 40? Would that would seem a reasonable assumption, right? You're expecting the answer to be a relatively nice looking number, which they are in most cases. But at least you'd be able to say, I'm darn sure it's dead close to 40, right? If you're not saying it's 40, you're definitely comfortable that it's very, very close to being 40, right? And that's essentially what the process does. We find numerical ways to estimate it, left 5 or right 5. And then once we do that, if we want a more accurate answer, we just up the number of strips. Human beings probably don't want to do more than about 10. Me personally, I don't want to do more than 6, right? But at least you know what it's doing when you go to a computer and you say to a computer, I want to find the area under this curve from 1 to 6. And the computer says, no problem, if computers could talk. I'll do 10 billion strips because I can do that in about half a second. And it pops out the answer. Aren't you comfortable that the answer is a good answer? Because doesn't the logic of this technique kind of means lots of strips, you're probably going to get a good answer, right? And the more strips, the better the answer. Well, that one was kind of very vague, a curve. I had to estimate these numbers. So let's take it and do it a little bit more accurate. Let's show you how to approach a real question. I'm going to pick a very simple curve, y equals x squared. And I would like to find the area under this curve from 0 to 2. And we call the start number, we use the letter A, and the finish number, we'll find that we typically call that B. I want an estimate for this guy. And I'm a human being, right? I'm not a computer, so don't tell me a million. But let's be practical. Don't tell me one strip either, right? So give me a number of strips. And if I don't like the number, I'll pick 9. But how many strips do you want? Keep it simple.
4.
I like 4. Would you agree that this splits into 4 nicely without weird decimals? So you're being told to find an estimate using n equals 4 strips, which is typically going to be told to you in the question, right? They don't let you guess. They say, I want 6 strips, I want 8 strips, I want 4 strips, right? They're going to tell you. Now, first thing you're going to find is how wide each of these strips are. So you're going to start at 0, you're going to finish at 2, and since you're going to break it into 4 strips, I think you can tell where the strips are going to be. Can you agree it's going to be at 0.5, 1, 1.5, and 2? But in general, this is how you calculate the width. It's the difference between the start and the finish divided by the number of strips. Now, in this case, that's kind of trivial because you start at 2 and you finish at nothing, and you divide by 4. And can you see the 0.5? So far, so good? Now, what I suggest you do in your homework, because you're going to do these by hand, is that you set up a little table. And 0 is your start. And then, because you know this is 0.5, you just keep adding 0.5s. And if you do it correctly, shouldn't you eventually finish at the last number, in this case 2? So that's how you're going to set up the table. So can you imagine in the future, this number isn't 0, it starts at 1, and maybe it's got 8 strips. So can you imagine you'll go 1, 1.2, 1.4, 1.6, 1.8, you know, you just go up in this number. So it's important that you've got this number because you know the start number and you know who delta x is. Won't that tell you these guys here, right? These x coordinates are given a couple of names. They're sometimes called the boundary points. They're sometimes called the endpoints. That's the 2 most common names I know of. So if you hear they're talking about the boundary points or the end points, they're talking about the 0s and the 1s and 1.5s and the 0.5, right? They're talking about those guys. So if you hear that term, that's what they're on about. Now, the value of the function is essentially the height of these lines, isn't it? Right? The value of the function at 0, 0 squared. Nothing 0.5 squared. 1 squared. 1.5 squared. 2 squared. And you fill that in. Okay? Because aren't these numbers going to be the heights of my rectangle? And what we're trying to do here is kind of set the thing up in a formal way so that it doesn't matter what the function's called or how many strips it's got. You're going to follow this process and it will get you to the answer that you're looking for. I'm going to move this over to here because I need more room. Now, there are only 2 guys in town right now. There are actually 5 altogether, but right now we're going to focus on 2 of them. We're going to focus on right 4 and left 4, right? So one of them, you use the left side to get the heights of the rectangle strips, and the other, you use the right-hand side to do it, okay? So for no particular reason, let's do L4 first. Now, if you're doing L4, I've got my guy here. I use the left-hand side, so that's not going to work too well because isn't the first rectangle 0 high? Now, if you use the next one, it's going to be there. The next one, it's going to be there. And the next one, it's going to be there. What does that look like in my table? That's going to be the height of the first rectangle. This number here is the height of the second rectangle. This number here is the height of the third rectangle. And this number here is the height of the fourth rectangle. Do you see it's much better if I've got numbers than trying to read off from some graph? Right, I've got real values. So if I'm going to do L4, isn't that the only numbers I need? The heights of the four rectangles. So what is the area of each of these strips? Well, the width is 0.5 times the height is 0. So that's the first rectangle. Then a width of 0.5 times a height is 0.25. The same width again, but the next height would be 1. And then the last, and the last one would be 0.5 times 2.25. Isn't that basically the area of the first, second, third, and fourth rectangles? Can you see the strips and the calculation? The first rectangle, second rectangle, third, and last. Now, these ones are so easy to do, I could just write them down. But can you imagine that these are really ugly decimals, like 1.234 and 8.7799, right? Wouldn't there be a lot of work in multiplying them and then adding them? But have you noticed that because each of them use the same first number, can't we pull that out as a common factor? And instead, can't we just find that fella? Would you agree that this calculation is the same answer as the one above? Would you also agree that maybe not this time, but in general, isn't it easier to just add up a whole load of numbers and multiply once than do an awful lot of multiplications and then still have to add them all up afterwards? Would you agree that's just a little bit less work? So if you are going to have to do them by hand, shouldn't we at least try and minimize what we need to do by hand, right? Now, in this particular case, it's going to be 0.5, and that plus that plus that plus that, I believe, is 3.5, and that guy gets me 1.75. Are you comfortable of how I found L4 in this question? Right. Now, suppose that was the ugliest function in the world, right? X cubed plus sine x all divided by the square of x plus 1, right? Something really massively ugly. I would still create this table. And you might say, well, how do I get the value of the function? Do I have to take this horrible function here, whatever it was, and evaluate it 5 different times? Well, yeah, you could do that and it would work. But there's a nice feature on your calculator. So I'm going to take a little side issue now and talk about how do you fill this table in when the function isn't something easy, when it's really ugly, right? How would we do that? And so here goes. I'm going to make sure my calculator's set for it, which it is. So what I'm going to do is I'm going to go into y equals, and I'm going to write down whatever that horrible function is. Now, I can't remember what I said last time, so I'm making up a new one. Couldn't it be x cubed multiplied by the sine of x, all divided by a square root of x plus 1? But you agree that's a massively ugly looking expression, right? Agreed? Now, I want to make a table starting at 0, right, and finishing at 2. And I want to find out what these numbers would be for this new really ugly function. So you go second table setup. Now, it has as the first thing table start. What number do you think on this question here, what number should be table start? Yeah, Matthew's doing a big circle, it's a 0. Now, delta table. What number is delta table? Or what decimal is?
0.5.
0.5. Do you see that that's basically the A and the delta X? Are we good with that? Now, Make sure it's set up as auto and auto, and that's you set up the table. Now you get the answer. Go blue button, table. And here are all the guys you want. Do you see them? And some I don't. Can you see that basically you're looking at the table, especially if you rub out those two guys? And isn't that kind of clever? Because hasn't your workload now been reduced by a lot because you've let the table feature on your TI-84 do some of the heavier lifting for you? Are you comfortable with that? How you can create this table for even the ugliest functions in the world? So let's return back to our puzzle. That's L4. Now L4 is made up of these. I'm going to have to make them a little bit more noticeable. Would you agree that if I'm using these 4 rectangles, that this answer is less than the real answer? Would you agree that these 4 add up to an area that's not as big as the real answer? We call that an underestimate. Very often, if you draw the thing or put it on your calculator and look at it, you can see whether something's going to be an underestimate or an overestimate. But you can also tell, because this function is increasing, that that's what we're going, we're going to get. Now I'm going to do the other choice. Now, if I was going to do the 4 strips again, I'm going to go back to the first one, but you see I'm going to take the right-hand side, so it's that green guy. And then it's going to be this green guy. And then it's going to be this green guy. And lastly, it's going to be that green guy. Now, well, green's probably a bad choice now, but never mind. Do you notice that I end up using the heights by using those 4 numbers? So do you notice that when you use an L4 and an R4, you only use 4 of the 5 numbers from the table? You can see in the first one, I used the first 4. Now, one way to remember this, or for me to remember it, see if I turn it on the side. Do you know when you do an R4, isn't it the 4 on the right you use? And when you do an L4, isn't it the 4 on the left? So that's a quick way of remembering which 4 do I use if it's an L4 or an R4. Right. Now, if I set it up the long way first and then abbreviate it, let's see what we get. The first rectangle is 0.5 times a height of 0.25. The second rectangle is 0.5 times a height of 1. The third rectangle is 0.5 times a height of 2.25. And the last rectangle is a height of width of 0.5 times a height of 4. And just like before, we got that. And that means I only need to add up these guys once. And what do I get? I get total 2.5, 3.5, 7.5. And that comes out to be 3.75. Would you agree that these green rectangles, which is what R4 is using, aren't they bigger than the real answer, right? The true answer? So we call that, not surprisingly, an overestimate. And now I know something. The true answer, right? The exact answer. Isn't it going to be somewhere between those 2 places? Hasn't it got to be bigger than the underestimate, but less than the overestimate? And that's a useful thing to know. Okay, I don't know exact answer, but can't I bet my money on it that it's definitely somewhere between 1.75 and 3.75? At least that I can tell. And I can only do that in some circumstances. Can you agree? You can only do it when you're absolutely sure that the left or the right is an under and the other one is an over. And so the only time you're allowed to do this over underestimate is when the curve that you're trying to find the area under, if it's always increasing, right, going uphill, or if it's always decreasing, going downhill. Can you imagine in those two situations, these are always going to be, one's going to be the over and the other's going to be the underestimate, right? But see if you have a curve that zigzags up and down, you can't really say this is an overestimate with any degree of certainty, or that it's an underestimate, right? You could do an eyeball and think, yeah, the rectangles are a lot bigger and the couple that are smaller aren't important enough. You could maybe do it by eyeballing it. But if you want to just be pure guaranteed math, you only use the under and over when it's an increasing or a decreasing part of the curve. I think we learned some cool stuff today. We now have a kind of framework. So when I see you tomorrow, we're going to do some boring stuff. And I don't like lying. So if I think it's boring, I'll tell you it's boring. You might love this stuff, and that's okay too. Because what we're going to do tomorrow is, here is a curve, find L4, find R4, and then find midpoint 4, which is one I haven't talked about. Any ideas how you're going to get the height of a rectangle if you do a midpoint 4?
Triangles?
Triangles ends up being connected to a fourth method called the trapezium rule. Midpoint. How do you think I'm going to get the height with a midpoint rule?
Average.
Very close to it. I'm going to use not the 0, not the 0.5, but the middle, the midpoint. I'm going to use the height of the rectangle at 0.25 and at 1.75 and at 1.25. Can you see that if I did that rectangle, wouldn't it be a bit of A and a bit of B? Wouldn't there be one piece of it below and the other piece above? So that would probably be a better estimate, wouldn't it? And that's called the midpoint 4. And Sabrina's triangle thing ends up being the trapezium rule. And that happens in section 7.7, I believe. And then there's one other technique called Simpson's rule, which is the ultimate trick for finding the area under a curve. And it's very, very accurate.